Thanks, everyone. Thanks for being here. It's my first time in Singapore, first Hack in the Box for me. It's been a pretty awesome conference so far. What I want to talk to you about today is something that I think is going to be pretty interesting. It's this idea of hardware backdoors, and that's sort of a concept that's thrown around a lot these days. It's often talked about in terms of conspiracy theories. A lot of people talk about Intel Management Engine and AMD Platform Security Processor as if they're hardware backdoors, but there's never really been any evidence that the things that we normally think about or worry about are actually hardware backdoors. So instead, what I'm going to be talking about is something entirely different than those normal things, something that I don't think was on anybody's radar, something that we really didn't know existed before this. But before I begin, the lawyers made me put in this very important disclaimer that I did all this work before I joined my current employer. I did all this on my own, and none of this work reflects my employer in any way, shape, or form. But beyond that, my name is Christopher Domas. I'm a cybersecurity researcher. I've poked around with a lot of different things over the years, but recently my interests have sort of been in low-level processor security, and that's sort of what we're going to look at today. But I want to start this whole thing off with just a little demo to frame the rest of the discussion here. So I've got a little video here. I'm logged into this system as a regular unprivileged user just called Delta, and then I'm going to open up this C file, and we're going to look at what's inside of this C file. It's basically a bunch of assembly code where I'm moving the address of a label into a register. And then I've got all these bound instructions. So if you're not familiar with the bound instruction in x86, it's not too common, but it's basically used to check whether or not a value is within certain memory bounds. So all of those bound instructions should fault because they're looking at nonsensical data. And sure enough, when I run my little demo here, after compiling it, the program faults, it crashes, nothing interesting happened. But then if I change one tiny little thing at the very beginning of this program, if I add one sort of secret x86 instruction, an instruction so obscure it doesn't even have a name, I have to write it out as raw bytes. If I add this OF3F to begin out the rest of my program, that's going to fundamentally change the way the rest of these bound instructions work. And now what they're going to be able to do is they're going to reach into the kernel and actually give my process root level permissions. So now when I run my demo and check who I am, I'm now the root user without even making any sort of API or system calls or anything else. We just sort of reached past all the privilege boundaries on this system in order to gain root access. So that kind of thing definitely shouldn't exist, but it's sort of fascinating that it's here, and that's sort of what the rest of the presentation will be on, is really how I found this this backdoor in this processor. And the whole thing comes down to the idea of what in x86 we call rings of privilege. So basically 30 years ago in the x86 architecture, there was no concept of separation of privileges. Basically any code that ran on the processor could have the exact same permissions as any other code running on the processor. And that was basically just chaos. It meant that like your calculator program could monitor when you were accessing your bank account because there's no separation between anything. But then x86 introduced this idea of rings of privilege that were going to separate pieces of code into different privileges. And the way this basically works is something like this. So at the center in ring 0, that's going to be your most privileged code. That's where the kernel and everything else that you really trust lives. All the things that actually have to have access to the physical hardware of the system are going to sit in ring 0. But then less privileged than ring 0 is going to be what we call ring 1. Less privileged than ring 1 is ring 2. And finally, in the outermost layer, we have ring 3. And that's where we're going to toss all our userland code, all of our regular applications and everything else, the stuff that we don't necessarily trust to have access to the hardware. Then the way this is going to work is when something in ring 3 actually wants to do something important, when it needs special permissions, it's going to have to follow a very careful, strict hardware-enforced set of security checks in order to ask ring 0 to do something for it. And that's the way things have worked for the last 30 years. We've separated our code into these different rings. Ring 0 has the most privileges. Ring 3 has almost nothing. But it's sort of interesting. Since this came out, things have continued to sort of evolve, and security researchers have continued to dig deeper into the processor. So eventually we sort of figured out that, well, if we want to run multiple operating systems on a processor, it doesn't work to have them all running in ring 0. We need something more privileged than ring 0 in order to separate out different operating systems, like the hypervisor. So we called that ring -1. Since the hypervisor has more privileges than the guest operating systems, that's sort of a deeper ring. And then x86 introduced this thing called system management mode, which actually was more privileged than the hypervisor, so we called that ring -2. And then about 10 years ago at Black Hat, some security researchers found this other processor running on some platforms that in many ways had more privileges than even the x86 processor, so they called that ring -3. So it's sort of interesting that ring 0 was supposed to be the most privileged layer on the processor, but we've continued to sort of dig deeper and deeper through the years. And I think in the back of any security researcher's mind who's been looking at this kind of stuff is always this question of, like, can we go further? How deep does this really get? So that's sort of the thing I was looking at when I set out to begin this research. And a lot of times when I don't know where else to begin on a project, I just start looking at patents to try to get some ideas on where my research might want to head. And I stumbled across this really interesting patent that had a couple of things that caught my eye. So just sort of casually mentioned in the middle of this patent I was looking at, it said, additionally, accessing some of the internal control registers can enable the user to bypass security mechanisms. For example, allowing ring 0 access at ring 3. Like, this just blew my mind that you would casually throw this out in a patent, because this basically undoes the last 30 years of x86 security. If you're telling me that there's some way to just allow the most unprivileged code to get the same permissions as the most privileged code in ring 0. They go on to say that in addition, these control registers may reveal information that the processor designers wish to keep proprietary. And for these reasons, the various x86 processor manufacturers have not publicly documented any description of the address or function of some of these control registers. So I thought this would be a really interesting thing to sort of dive into. They're basically hinting at this idea in the patent that there's some way to circumvent 30 years of privilege model in x86 through some undocumented control registers. So at this point, I didn't know where to begin. So I went out and I bought like 50 different computers to start researching. Now, based on the patent owner and time frame, I had some idea what processor I wanted to look at for this. But I figured it's always good to sort of cast a wide net in this case. But then when I started poking around on these different systems, I sort of narrowed in on the VSC3 processor. So this was a processor that came out about 20 years ago at this point. And it's used in a lot of interesting applications. It's mostly targeted at the embedded market, so you can find VSC3 x86 processors and point-of-sale systems, kiosks, ATMs, gaming, digital signage, healthcare, digital media, industrial automation. And you can also find these in PCs and laptops, especially low-power PCs and laptops that were coming out at the time. So eventually the system I selected for this research is this little thin client here that's using a VSC3 Nehemiah core processor. So the rest of the stuff I'm going to talk about was all done on this specific system. So for this processor, I wasn't able to find a developer manual. Like Intel and AMD release processor developer manuals. I couldn't find anything like that for VIA. So we sort of have to approach this thing as a black box and sort of try to follow a trail of patent breadcrumbs in order to figure out how to approach this research. So I basically kept looking at more and more patents from the manufacturer that came out around a similar time frame in order to try to gain information about this system. Unfortunately, sifting through patents can be really, really, really tedious work. So this isn't a patent I actually used on this research, but this was one I was sort of exploring along the way. And just to sort of highlight how awful some of this can be, I wanted to give a quote from one of these patents. It says, "Figure 3 shows an embodiment of a cache memory. Referring to figure 3, in one embodiment, cache memory 320 is a multi-way cache memory. In one embodiment, cache memory 320 comprises multiple physical sections. In one embodiment, cache memory 320 is logically divided into multiple sections. In one embodiment, cache memory 320 includes 4 cacheways, i.e. cacheway 310, cacheway 311, cacheway 312, and cacheway 314. In one embodiment, a processor sequesters one or more cacheways to store or execute processor microcode." Like, there's so much legalese here. That phrase, "in one embodiment," appeared 142 times in this 4-page patent. Like, reading through this kind of stuff, trying to gain information for research is really, really painful, but eventually it can pay off. So I settled on these 6 patents that ended up having some really interesting, useful information for sort of guiding this research forward. So I wanted to introduce some of the terminology that these patents were hinting at. So one of the main ideas discussed in these patents is the idea of using a non-x86 core alongside the x86 core in a processor. And they hint that the non-x86 core is going to be a RISC architecture. Now, they didn't have a term for this non-x86 core, but I started calling this the deeply embedded core in my research. The patents also hinted at something that they called the global configuration register. It'd basically be a register exposed to the x86 core through what's called a model-specific register, or an MSR. So I'll talk about MSRs coming up. But basically, they were saying that you could use this global configuration register to activate this embedded RISC core. They also talked about an x86 launch instruction. It was basically going to be a new instruction added to the x86 instruction set architecture, where once the RISC core is activated, this launch instruction would start a new RISC instruction sequence. So putting all these things together, then, if our assumptions about this deeply embedded core are correct, then theoretically it could be used as sort of a backdoor. Basically, would give you some way to surreptitiously circumvent all of the processor security checks. But then the first question is, if this thing really exists, how do I even activate it? So let's look at how we can figure that part out. Well, there's 3 patents that give us some hints as to how we could activate this deeply embedded core, as to how we could activate this backdoor. So one patent talks about a model-specific register that can be used to circumvent processor security checks. One patent talks about a model-specific register that can be used to activate a new instruction in x86. And one patent talks about a launch instruction that can be used to switch to a RISC instruction sequence. So if you put those 3 things together and sort of fill in the gaps, then it looks like there is maybe an MSR bit, model-specific register bit, that is going to enable a new instruction that will activate this secret RISC core and then bypass security protections on the processor. So let's look at the first piece of that chain. Let's look at these model-specific registers. So if you're not familiar with MSRs in x86, basically they're 64-bit control registers that do all sorts of different things on the processor. So they control things like debugging and performance monitoring, cache configuration, feature configuration. Basically anything that's not general computation can get thrown into a model-specific register. And unlike the registers that we're probably more familiar with, like EAX or EDX in x86, MSRs are actually accessed by address, not by name. And the addresses range from 0 to 4 billion. And then what you use is these read MSR and write MSR instructions in order to access the model-specific register. Now, there's a catch with MSRs, and that's that they are only accessible to ring 0 code. So our whole speculation about this backdoor is sort of predicated on this idea that the whole thing's activated through an MSR, which means that you have to have ring 0 access in order to activate this backdoor to begin with. So that should make this a lot less devastating, but that may or may not actually be true. So we'll revisit this ring 0 caveat later on, but just so that the research can move forward, we're just going to assume right now that we have one-time ring 0 access on this processor in order to activate the backdoor, and then I'll revisit this again later on. But sort of looking at where we should approach these MSRs, the patent kind of comes right out and tells us that the various x86 manufacturers have not publicly documented any description of the address or function of some control MSRs. So that means we're sort of forced to look at this thing as a black box. Like, we don't know what MSR we're going after here. So I want to figure out like which MSR bit and does something new on the processor, but that's not a whole lot to go on. But step 1 might be just figure out which model-specific registers actually exist on the processor. So not just which ones are documented. I want to figure out all of the MSRs that exist on my processor. So the approach for this is actually pretty straightforward. Basically, in x86, what you can do is you can create a new exception handler for the general protection exception, and you can do that through the LIDT instruction. After that, you're going to load your MSR address into the ECX register. And then you're going to try to access the MSR. So for example, if I wanted to figure out, does MSR hex 1000 exist on this processor, I load 1000 into ECX and then use the read MSR instruction. Now, one of two things can happen at this point. Either the read MSR instruction won't fault, which tells you that this MSR does exist, or the read MSR instruction will fault, in which case your exception handler gets control, which tells you that this MSR really doesn't exist. So we can basically enumerate all of the MSRs on the processor using this approach. When you do this, you end up finding 1,300 implemented MSRs on the processor, which is actually way, way more than most x86 processors would have. And that turns out to be far, far too many to actually sift through and try to analyze one by one. So we need, at this point, some way to pare those down into which ones I actually want to research, which ones are actually interesting on the processor. Namely, I want to figure out which of these 1,300 MSRs are really unique. So I had this idea of a timing side channel that could help with this problem. Basically, what you would do in this is calculate the access time for all 4 billion possible model-specific registers on the processor. And the way you can do that is you've got one of these read MSR instructions, and then on either side of that, you've got a serializing read timestamp counter instruction that lets you see exactly how long it took that read MSR instruction to actually execute. And when you do this and run this on the processor, this is actually what you end up with for these MSR access times. So basically what I'm doing is I'm trying to read each of the 4 billion MSRs on this processor one by one and looking at how long it takes to access that MSR. And this is what we end up with. So this actually is really interesting. It gives us a lot of insight into sort of the internals of the processor that we normally wouldn't be able to see. So there's sort of an observation that we can make by looking at these access times, and that is that functionally different model-specific registers should have different access times. So for example, reading a thermal sensor model-specific register should take a different amount of time than reading the timestamp counter model-specific register, and that's because when we execute that read MSR instruction, the microcode has to do something for that specific MSR. Since the microcode is going to be different for different or functionally different MSRs, it should take a different amount of time to execute. On the other hand, functionally equivalent model-specific registers should take approximately the same amount of time to execute. So for example, in x86, there's something called the MTRRs, the memory type range registers. It's a set of model-specific registers that control caching behavior for different regions of memory. There's a whole set of these MTRRs, but they're functionally doing approximately the same thing. They're all just controlling caching behavior. So since the microcode behind all of those MSRs is functionally equivalent, we would expect accessing those MSRs to take about the same amount of time. What that lets you do is it lets you differentiate between like and unlike MSRs. And we can define like a like MSRs as a set of adjacent MSRs with equal or functionally related access time. So from that, we can make this hypothesis that the global configuration register, this MSR hinted at in the patents that we're searching for, is probably unique. What I mean by that is it probably doesn't have multiple functionally equivalent versions. There's probably exactly one of these global configuration registers on the processor. So then what I can do is I can look at that timing side channel and I can try to pick out which of these MSRs based on their timing patterns are functionally unique. In other words, I'm going to select things like these peaks in each situation as functionally unique MSRs. And when we do that, we can identify 43 unique MSRs out of the 1,300 that are actually implemented on the processor. So that's a big step forward. 43 is a much more tractable number of model-specific registers to analyze than 1,300. Unfortunately, it's still a pretty daunting task. I think one of the bits in one of these model-specific registers is going to enable this alternate core on the processor, but each of these registers is 64 bits wide. That means I still have 2752 bits to check. And what I'm trying to do is I'm trying to figure out which of these bits is going to activate this new x86 instruction, this launch instruction that the patents hint at. So in other words, what I kind of want to do is I want to activate one of these MSR bits, and I want to scan through the x86 instruction set to see if any new instructions have appeared. But x86 is a really, really complex architecture, and it's sort of hard to estimate exactly how many instructions there could be in x86, but you can put an upper bound on it. So by looking at the x86 architecture, there's potentially somewhere on the order of 1.3 undecillion x86 instructions out there. And I'm trying to find exactly one new instruction amongst all of those. So even if we had like a really, really generous estimation, if I could scan for 1 billion x86 instructions every second, we could do a quick Fermi approximation here. If we look at like 1.3 undecillion possible instructions divided by 1 billion instructions a second, divided by 60 seconds a minute, divided by 60 minutes an hour, divided by 24 hours a day, divided by 365 days a year, means it's going to take about an eternity to scan for one new x86 instruction in the architecture. But then we're not even dealing with just one scan. I've got 2,752 different bits to check. So I'd need to do 2,752 scans of the architecture to figure out which of these bits creates a new instruction. So obviously we don't have time. Like, this is not a tractable problem at this point. So fortunately, last year I developed a tool exactly for this problem called SandSifter. So it uses some x86 magic in order to sort of intelligently try to scan the x86 instruction set. And it doesn't scan all instructions, but it tries to find the likely instructions that exist on a processor. And it can do that in about a day of scanning. Now, I still can't run SandSifter 2,752 times. That's going to be years and years of scanning still at this point. So what we can do is something a little bit different, trying to find this launch instruction. What I'm going to do is, for each of those 2,752 bits that I'm interested in, I'm going to try to set that bit. Basically, just see if I can activate it, not scan the instruction set or anything else, just try to set that bit. There's a problem with that, though, right away. Basically, these are configuration bits on the processor that aren't documented, and I don't know what they do, but a lot of them are doing very, very detailed internal things on the processor, which means that a lot of bits, if you just try to set an arbitrary model-specific register bit, will lock or freeze or panic or reset the system in some way. So I can't really do this manually, trying to toggle each of these bits one by one. We need some sort of automated approach to help us figure out which of these bits are actually can be set. So I developed a little system for helping with that, where basically I would have the target system that I'm trying to research connected to a switch. Connected to a master system. And that master system is connected to a relay, which is connected to the power button on the target system. So what the master system is able to do is it SSHs into the target system and tries to activate one of these model-specific register bits. If it detects that it has corrupted the target system in some way, if the system resets or freezes or stops responding, it can then use the relay in order to reboot the target system. So in this way, what I can do is I can sort of automatically try to set these bits one by one, and I can reset the system when something goes wrong. So basically just describing what we just went over. So when you do this, you run this system for about a week, just continuously reset the system whenever you find an MSR bit that you couldn't toggle. Basically what we're able to do then is find exactly which bits can be toggled without a visible side effect. So we can go through and then try to toggle all of those MSR bits, and only then run the actual SandSifter scan in order to audit the processor for new x86 instructions. So what that looks like is something like this. This is SandSifter scanning the processor for new instructions. I'm starting SandSifter in the middle of a scan so that we can see it find something fairly quickly. But basically we're just using page fault analysis and a depth-first search in order to find the probable instructions that exist on this processor. And then down here, SandSifter is going to spit out any anomalies that it finds. And if we let this run for about a day, we'll eventually see SandSifter spit something out here. Basically, it was able to identify exactly one new instruction on that processor after all of the model-specific register bits were toggled. It finds this OF3F instruction that shouldn't normally be there. So using GDB and a little bit of trial and error, we can find that this OF3F, this launch instruction that the patents are talking about, is effectively a jump to EAX instruction. So now that we know what that launch instruction is, we no longer need to run complete SandSifter scans for each of these individual MSR bits. Basically, I can now toggle MSR bits one by one, see if OF3F executes. If it doesn't, that's not the MSR bit I'm looking for. If it does, then I found the bit that enabled the launch instruction. So using this approach, we're able to figure out that MSR number 1107 bit 0 is the one that activates this launch instruction. So MSR 1107 must be the global configuration register then that the patents were talking about. And that leaves us with this bit 0. Basically, what we suspect is that through that MSR, we are enabling some mechanism that's going to unlock the processor and circumvent all the security checks on the processor. So I called that MSR 1107, that bit 0, the God mode bit on this processor, since it would sort of unlock complete access to the system. So now we've found this God mode bit. We've found this launch instruction that should enable us to execute instructions on the other core. The question then is, how do I actually execute instructions on this RISC core? And the patents can sort of give us some insight there. They sort of suggest that there's a place in the processor's pipeline where it will split between either doing x86 execution or doing RISC execution. And through some trial and error, I sort of came up with this model for what that looks like in the pipeline. Basically, it looked like there'd be an instruction cache. An x86 instruction will get fetched from the instruction cache and passed to some sort of pre-decoder. And what the pre-decoder is going to do is it's going to break apart that x86 instruction into its individual components, like the opcode or the mod RM byte or an immediate value. And then it's going to pass all of those components to some check. That check is going to see if you're in RISC mode or not. And if you are, it's going to pass one of those components, in this case a 32-bit value, over to the RISC decoder. If you're not, it's going to pass all those components over to an x86 decoder. So I sort of found this model just through a lot of trial and error and testing. But with this setup, that basically means that there is some x86 instruction out there where if the processor is in RISC mode, then it can pass a portion of itself onto the RISC processor. So now my question is, what is that instruction? Since that instruction sort of joins these two cores, since it acts as an intermediary between the x86 and the RISC core, I started calling this the bridge instruction. This instruction that would let me send commands over to the RISC core. So now the question is, how do I find the bridge instruction on this processor? Well, it should be sufficient to detect that I've executed a RISC instruction. If I have successfully executed a RISC instruction, then I know what instruction I used in order to do that. So then the question is, well, how do we know if we've successfully executed a RISC instruction? Well, if this RISC core really does provide a privileged circumvention mechanism on the processor, then there should be some RISC instruction that when executed in ring 3 should be able to corrupt the system. So normally that would never happen in ring 3. The whole purpose of the separation of privileges is that you can't corrupt the system from ring 3. But if we can circumvent those privileges and observe that behavior, then that means that we've found this RISC instruction. So this is actually really easy to detect. Basically, if we're executing instructions in ring 3 and we detect that the processor has locked or the kernel's panicked or the system has reset, then that means that we've found this bridge instruction. We've successfully executed an instruction on the RISC core to corrupt the system. So I used SandSifter for this again. I basically tore out the guts of the SandSifter fuzzer and ran it in a brute force mode and modified SandSifter to execute the launch instruction before each x86 instruction that it tried. And basically what SandSifter is trying to find now is the exact right combination of an x86 instruction and a corrupting RISC instruction to cause a processor lock or a kernel panic or a system reset. So that's going to look something like this. Basically, we've got a dumbed down version of SandSifter brute forcing instructions on the processor, basically running in ring 3 and trying to cause a system lock. And that's what we got here. Basically, everything on the system just stopped all of a sudden because SandSifter was able to find a specific x86 instruction that when run in ring 3 corrupted the system, which should never happen. So basically when we've observed that, that means that we've found this bridge instruction that we're looking for. So it took about an hour of fuzzing with SandSifter here in order to identify the bridge instruction as this bound EAX instruction. So basically this is the x86 instruction that is able to send commands over to this deeply embedded RISC core. And then there's this middle part of the instruction, this 32-bit value here. It turns out that that 32-bit value used in the bound instruction is the RISC instruction that is going to be sent over to that RISC core. And that's a pretty easy thing to check. Basically, just try out different 32-bit values here. You'll see that some of them always lock the system and some of them never lock the system, which is a pretty good indicator that that 32-bit value is actually the RISC instruction that's being sent over to the deeply embedded core. So now we're to the point where we know how to execute instructions on the deeply embedded core. The question then is, what do we want to actually execute? Basically, I don't know what these instructions look like. I don't know what architecture I'm dealing with for this deeply embedded core. So we need to figure out that part next. So an obvious first step is to sort of assume that this RISC core is just some sort of common architecture. It doesn't really make sense to reinvent the wheel. So I assumed going in that this was just going to be ARM or PowerPC or MIPS or something like that. So we can basically just try to generate instructions in some common RISC architecture and try to execute them on the RISC core and see what happens. So for example, if I wanted to see, hey, is this an ARM core? I could generate a very simple ARM instruction like add 1 to R0 and try to execute that and see what happens. The challenge with this approach is the RISC core probably has registers that aren't even accessible to the x86 core, which means that there's no obvious way to check for the effects of the instructions that you're trying to execute. So for example, looking at the last slide, if I did execute this add 1 to R0 instruction, how do I even observe R0 from my x86 core? So my solution to this was sort of an observation that even though I might not be able to easily observe most of the effects of my instructions, I should still be able to rule certain architectures out. Basically, what I found is that a lot of the instructions I was sending over to the RISC core would cause the processor to lock. So that's one of the few visible effects of these instructions that I could actually see. So basically, what I could do then is just execute really simple non-locking instructions for each architecture. So like add 1 to R0 for ARM. And then when I execute that on the RISC core, if I observe that the system is locked, I can sort of infer that, well, that must not have been an ARM core if add 1 to R0 corrupted the system. So using that approach, I ruled out 30 different possible architectures. So we're sort of in a tough spot at this point. I still think this is probably based off of some known architecture, just been modified too much in order for me to understand it. So we sort of have to approach this now as a black box, as some sort of unknown architecture in this deeply embedded core, which means that we're stuck with the prospect of trying to reverse engineer the format of these deeply embedded core instructions. So I spent enough time dealing with this that I gave this its own name. I started calling these instructions the deeply embedded instruction set, or the DICE. So how does that work? How can we reverse engineer a completely unknown instruction set? Well, basically, my thought was we could execute a RISC instruction and try to observe its results. But like I said earlier, we don't really know what this RISC ISA actually looks like. So I don't really have a clear way of observing the results on the RISC core. But fortunately, some of the patents give some insight into this. The patents actually hint at the idea that the RISC core and the x86 core have a partially shared register file. So I might not be able to observe all of the results of my RISC instructions, but I should be able to observe some of the results from the x86 core. So the patents, as an example, illustrate an x86 core and an ARM core with a partially shared register file. So that helps. That means that we should be able to reverse engineer at least some of this instruction set. So what this would look like is we would toggle the God mode bit. Remember, that's the part we do need ring 0 access for now, just toggling this bit. We're going to do that through a loadable kernel module. And then I'm going to generate some sort of input state for the processor. Basically, I'm going to select values for all the processor registers. I'm going to create some buffers in userland. I'm going to create some buffers in the kernel. And I'm going to record all of those values. Then I'm going to generate a random RISC instruction. I'm going to wrap that RISC instruction in the x86 bridge instruction, and then I'm going to execute the RISC instruction on the deeply embedded core by preceding it with the launch instruction. That should execute the RISC instruction, at which point I'll record my new processor state. I'll record the state of all those registers, the buffers, everything else that I had originally set up. And then I'm going to look through for differences in the processor state. So that looks something like this, sort of a summary, where in this initial block here, I'm setting up the input state. I'm basically loading all the processor registers with some predetermined values. I'm creating buffers in the userland, buffer in the kernel. After that, I've got this OF3F byte. That's the launch instruction, which is going to enable me to send commands over to the x86 core. Then I've got this bound instruction here, and that bound instruction has that 32-bit value in it, and that's the RISC instruction that's actually going to be executed on the deeply embedded core. So then, after that instruction executes, what I'm going to do is I'm going to look at my new processor state, and I'm going to see if anything changed between my input state and my output state. So I basically turned this concept into a fuzzer where it would look for certain basic patterns by generating specific input and output states. So a challenge with this, one we've encountered before to some extent, is we've got this unknown instruction set with unfettered access to ring 0, which means it's really, really easy to accidentally generate instructions that are going to cause a kernel panic or a processor lock or a system reboot. And in practice, what I found is I could only execute about 20 random RISC instructions before there was some sort of unrecoverable corruption on that system, and then I had to reboot the target. But even after optimization, it took about 2 minutes to reboot these systems, and some quick calculations showed that it was probably going to take months and months of fuzzing to collect enough data to actually reverse engineer this deeply embedded instruction set. So I decided to expand my system from earlier. So instead of just one target hooked up to a master, I bought as many of these systems as I possibly could and hooked them all up to this master system. And the overall system ended up looking something like this, where down here I've got my 7 targets that I'm attacking. You can see a little green wire coming out of the chassis of each of those. That's a wire hooked up to the relay in the upper left-hand corner. That's how I'm going to be able to power cycle these when they freeze. That relay is hooked over USB to this master system. All the targets network boot from the master, and the master can SSH into the targets in order to give them specific fuzzing jobs. So basically summarizing all that work. So we can actually see this thing in action. What I'm going to do is I'm going to start a job on the master system. The master is going to think for a little bit and try to figure out how it's going to task the individual targets, basically what fuzzing jobs it wants to give to each individual target. And then it's going to start powering up each individual target. If you look at the relay in the upper left, you can see the relay toggling each of these systems one by one. Down here, you can see the green lights on each target coming on one by one as these systems boot. And then we wait basically for the systems to boot. So I'm going to fast forward a little bit through that so that we can actually see what we do once the systems come online. Basically what the master is going to start doing at this point is tasking each individual system with certain fuzzing jobs. So you can see state diffs starting to scroll by on the master. Basically when it observes a difference in the input and output state, it's going to record that information. When it observes that one of the systems has locked, you could hear just a second ago the relays toggling. Basically, it's power cycling each of these systems whenever the system becomes unrecoverably corrupted. But basically, we're just going to let this run for quite a long time. And we can sort of see logs scrolling in from these systems and basically just recording state diffs each time. So I let this run for 3 weeks. It collected 15 gigabytes of logs across 2.3 million state diffs for a total of about 4,000 hours of compute time. So it's a lot of data that it collected. But now that it's done collecting its data, we can actually start looking into these logs to try to figure out how this unknown instruction set actually works. So the very first thing I wanted to figure out is my premise correct? Can this thing actually bypass the rings of privilege in x86? And much to my relief, after all this work, it's pretty quick to go through these logs and figure out that is actually the case. So for example, in this log, you can see the input and output state differed in the EDX register. Specifically, we see this value 80050033 in EDX. That turns out to be the control register 0. Now, CR0 is normally not accessible to ring 3, but we can see that through this RISC instruction, we managed to access CR0 through this up at the top A771 RISC instruction. So that's a good sign. I'm able to read ring 0 data, or registers that are normally only accessible to ring 0 from ring 3. So then the question is, well, am I only limited to reading ring 0 data? And it turns out not. If we keep going through the logs, we'll see this other instruction, 8AB4, is actually able to copy the EBP register into debug register 0. So debug register 0 is normally only writable to ring 0. So I'm actually able to write ring 0 only data using this deeply embedded core. So at this point, the question is, what do we want to do? Well, theoretically, this thing can bypass all the ring boundaries, which means we can do anything we want on this processor at this point. But I thought it makes sense to try to come up with a sort of a succinct, simple demo to really illustrate the power of this deeply embedded core. So I thought a good demonstration would be a privilege escalation payload, basically something that would take an unprivileged user and grant them root permissions all from within ring 3. So a privilege escalation payload from this deeply embedded core perspective would look something like this. Basically, you can parse a structure in x86 called the global descriptor table. And inside of the global descriptor table, there is what's called a segment selector for the FS segment. If you parse out that segment selector, you can get a pointer to a Linux structure called the task struct. And if you parse out some of the task struct, you can get another pointer to what's called the cred struct, all this sitting in kernel space. Finally, inside of that cred struct, are 4 fields, the UID, GID, EUID, and EGID, that define what permissions your current process has. And if we set all of those 4 fields to 0, that's effectively giving our process root permissions. But all this can only occur from within the kernel normally. But basically, we want to implement this functionality using the deeply embedded core. Now, there's only a few pieces in here that actually require us to bypass the kernel boundaries. We don't have to do all of this on the deeply embedded core. It's only these key pieces that actually reach into kernel memory. But I thought it's sort of fun trying to write programs for this secretive core on the processor. So I kind of wanted to try to do this entire thing from within this deeply embedded instruction set. So at this point, it's sort of like building a ROP chain. Like when you're building a ROP chain, you've got a set of primitives to work with, and you sort of sift through these primitives trying to figure out how to construct higher level functionality, which is basically exactly what we have here. We've got 15 gigabytes of logs, and we want to sift through these logs to find some primitives to build up this payload that we're after. So the first thing we might want to try to find is a GDT read, some way of reading the global descriptor table. So we can find that pretty quickly. Instruction A313 is able to load the global descriptor table register into the EBX register. Next primitive we might want is a kernel read. We can find that, D407. We can see that it loaded a single byte out of a kernel buffer into the EBP register. We need a kernel write primitive, and we can find that in E2B7. We can see that it wrote a single byte out of ECX into my kernel buffer. So we've sort of got all the building blocks we should need. If we want to write this entire thing in the deeply embedded core, we need primitives like addition. These are a little bit harder to spot when you're just manually going through logs. So it's not immediately clear that an addition occurred here unless you're very, very tediously analyzing all the other registers in your input and output state. So you can try to fix that by adding some patterns to your register. But at the end of the day, I sort of came to the conclusion that sifting through logs like this just doesn't scale well. So I wanted some sort of automated approach to reverse engineering this instruction set from these logs. So basically what I wanted to do was extract behavior patterns from these state diffs in order to identify patterns in the RISC instructions. So I built this tool that I called the collector that sort of does automated reverse engineering of unknown instruction sets. So basically what the collector does is it tries to automatically identify patterns in state diffs. So it'll look for patterns like word swaps or word copies or immediate loads or register transfers or memory reads or memory writes or increments or decrements. Basically it has this whole library of patterns that it will search for in these state diffs. And it will start binning instructions based on the patterns that it's finding. And after it ends up with an instruction bin, we can start trying to automatically extract the instruction encoding by analyzing bit patterns within the bin. So that looks something like this. Basically, this is the bin of all the instructions from my logs that were observed to transfer one register to another register. And the question for the collector is, what does this instruction format actually look like if I want to be able to write these instructions myself. So with a little manual analysis, I saw EAX register is always encoded as 0000, ECX is always encoded as 0001. So the collector can then go through for each of these instructions. It can try to find exactly which bits might be encoding the registers. So for example, for this instruction, we're highlighting all the bits that could be encoding EAX and all the bits that could be encoding ECX. So then it's going to go through this pattern and try to find out, well, what are the commonalities across this entire bin? Well, it turns out only these two center columns are common for all of these instructions. So those must be the bits that are actually used to encode these registers. It can do things like trying to extract the opcode bits from these instructions. So basically looking at bits that are similar across the entire bin. And it's not a perfect process. You can see ideally what we would like to see is all of these instructions using perfectly consistent opcode bits, but we don't see that here. We see this top half using pretty consistent opcode bits and the bottom half doing some different things. What the collector does is it just tries to find the most common patterns. So it's going to say, well, we'll just use the patterns from this top half here, and we'll call these highlighted bits the opcode bits. We can look for statistical patterns in bits in order to find don't care bits or bits that might be doing something that we don't fully understand. And then it mashes all this information together in order to derive an encoding for, in this case, register transfer instructions. So basically this is what the collector ends up finding for all of the individual primitives that we might want to implement in our assembly, like the load global descriptor table and move. It ends up with these bit-derived encodings. And it's not a perfect process, but for all of the purposes we need it for, it does all the work for us, basically. And we end up with this deeply embedded instruction set that can do exactly what we need. So there's some more information in there if you're curious about exactly what these instructions look like. But I basically threw all of this stuff into a custom assembler for this deeply embedded instruction set that I called the DICE assembler. Basically, it lets us write payloads in a higher level assembly representation and then assemble them down into their raw form. And the assembler is going to wrap each of those RISC instructions in the x86 bridge instruction so that we can send it from the x86 core over to the RISC core. So at this point, our payload looks something like this. We used the RISC instruction LGD in order to grab the global descriptor table. We used some of our other instructions that we identified in order to pull out the FS selector, use some other deeply embedded instructions in order to parse that. We grab the pointer to the task struct, grab the pointer to the cred struct, and then reach across kernel privilege boundaries in order to grant ourselves root permissions. So collectively, our payload looks something like this, where on the left there, at the top, we're unlocking the backdoor using that launch instruction, and then we've got all of our bound instructions sending commands over to the RISC core before we finally launch a shell. So we can revisit this initial demo at this point, now that we understand exactly how this thing works. So basically what we saw at the beginning was using the x86 launch instruction in order to activate the RISC core, and then using all these bound instructions in order to send specific commands over to the RISC core. So our payload is essentially encompassed in immediate values in these bound instructions. So effectively, that's how, when we compile this thing and run it, we're able to reach across the ring boundaries on the processor in order to grant ourselves root permission. So I sort of had this slide in here as a tongue-in-cheek slide. So at this point, the whole idea of rings is becoming very nebulous, and it's sort of silly to keep thinking about, are there deeper things than ring 3? But in a way, this is sort of a ring minus 4. It can do a lot of things that we normally call ring minus 3 can't do. So for example, from this deeply embedded core, we have unrestricted access to the x86 core's register file. We've got a shared execution pipeline. But at this point, like I said, it's sort of nebulous, and the point's moot whether or not this is any more powerful than what we've seen before. But at the end of the day, this does give us direct ring 3 to ring 0 hardware privilege escalation on x86, which to my knowledge has never publicly been done before. But fortunately, we should still need ring 0 access in order to activate this whole thing to begin with. Remember, we had to set that God mode bit using one-time ring 0 access on the processor, at least theoretically. It turns out that that's actually not the case. So what I've got here is a different VSC3 processor. This is Samuel 2-core VSC3, and I'm freshly booting this system. So nothing else is run on this system right now. And I'm just going to log in as a regular user. And I don't have the right tools installed on this. I don't have read MSR and write MSR tools in order to check these model-specific registers. But what we can do is we can fast forward this a little bit. I can use modprobe to install the MSR kernel module, and then I can use a hex dump in order to look at that global configuration register, MSR number 1107. So I'm going to dump out the contents of the global configuration register. And if you look closely at the low byte of that register, it's D7. The low 4 bits, the low nibble is 0111. That means the low bit, the God mode bit on this system is 1. This system just freshly booted, but the God mode bit is already active by default. That means on this system, any unprivileged user can escalate to the kernel at any time without ever needing initial ring 0 access on that system. So that's a scary prospect, because when you totally break down the ring privilege model on x86, when you can just bypass that arbitrarily, all the other defenses that we have ever developed for these systems become obsolete. Like antivirus does nothing anymore. ASLR depth, they don't help you when you can just reach directly into ring 0. Things like code signing, control flow integrity, kernel integrity checks are all sort of blown away when there's no more boundaries, when there's no more separation between ring 3 and ring 0. There are some mitigations we could consider for something like this. You could try to update the microcode on the system to lock down that God mode bit so that it wasn't active by default. You could update the microcode to disable ucode assists on the bridge instruction so that you couldn't send commands over to the deeply embedded core. Updating microcode is kind of cumbersome and not necessarily the best solution. It could also be possible to update your operating system and firmware to disable this God mode bit and then periodically check it to make sure nobody's activated it. But at the end of the day, those are probably not necessary. This is a very old processor, and it was never in very widespread use, at least not in computers or things like PCs and laptops. It's not terribly common. And I don't want to throw VIA under the bus here. Their target market with this processor was embedded. I don't think they were doing anything malicious with this feature. I think this was probably a useful feature for their customers and just had a very poor implementation with a lot of very unintended side effects. And then I think the part where it gets really interesting is after I released this research, some people in the community were actually able to dig up an old data sheet for this processor. So it's not actually directly available from VIA. It's available on an archive data sheet website along with a bunch of other NDA'd VIA documents, which makes me think that this was never released to the public to begin with. But buried in that data sheet, there's sort of this passing mention to MSR 1107. That's the MSR that we're interested in, bit 0, as activating an alternate instruction set. So what I was calling a deeply embedded instruction set, they're calling the alternate instruction set. But then they go on to basically say, if you have a justified need to access these instructions, you need to contact your VIA representative. So basically, for all intents and purposes, this was undocumented. That might have helped us save about 25% of the research if we had known which MSR bit to start with. But I think this does make it look good for VIA. It kind of shows that this was not malicious functionality. It's a functionality with unintended side effects. So at the end, I think we should take this sort of as a case study. The reality is backdoors do exist. It's not just conspiracy theory stuff. This is a real problem. But even when we're dealing with black box systems, we do have the capabilities to find these kinds of things. So sort of looking forward, even though this is just one old chip, I think the idea of hardware backdoors is absolutely devastating and sort of forces us to rethink our models on security. So that's sort of where I want to leave this, as basically a thought experiment on what backdoors might look like and how we might find them even in a black box approach. And because I do think like this is a really big problem. This isn't just a C3 problem. It's not just a VIA problem. It's not just an x86 problem. I think this is a problem that sort of pervades all of computer engineering, that these pieces of hardware that we are trusting to do all of our computation and hold all of our secrets, we have no way of introspecting them. We have no way to make sure that they're actually doing what we think they're doing. So I think whether or not hardware backdoors exist in other things, the possibility is going to continue to haunt us until we have a way of introspecting our hardware. So I don't know what the answer is to this, but I can tell you, like, the patents that I was looking at, or that I showed here, are really just the tip of the iceberg. There are a lot of scary things just sort of casually hinted at in some of the patents that I was coming across. So what I hope is sort of moving forward, that what we'll do as a security community is really anytime we see a secretive feature or something that's not fully documented, that should be a big red flag. That should be something that we push harder on and dig deeper into, because that's sort of how we can start to actually build trust in these systems. That's how we can start to overcome this problem of black box hardware. So along those lines, I've open sourced all of this as what I'm calling Project Rosenbridge. Basically, all the tools and techniques, the code and the data that I've illustrated here are now available online. And I'm really hoping that people will be able to use this as sort of a jumping off point for deeper processor security research. I think a lot of the ideas shown here are not unique to the VSC3. They're things that we can apply to modern processors right now. And I hope that we can use these to sort of dig deeper and see what processors are really doing. So all of this is available on GitHub, github.com. My handle is XOR-EAX. This is called Project Rosenbridge. There's some other interesting stuff on there, like we used the sand sifter scanning tool throughout this research. So that's all open sourced on there as well. I just uploaded a bunch of fun projects from the past there. There's a single instruction compiler, some neat control flow stuff, another x86 exploit from a few years back. All that's on there, and I really hope people will look at that and more importantly, build off of it to sort of see where we can take these possibilities. So I really love talking about this stuff. If you've got any feedback or ideas on this or any of the other research that I showed, I'd love to talk to you about it, either over lunch, which is coming up in just 2 minutes now, or you can reach out to me on Twitter. Again, my handle is XOR-EAX, or same thing at gmail.com. Or of course, I'll be around the conference for the rest of the next 2 days. So thanks everyone for attending, and I think it's lunchtime now.